All right, I hope we're back in business with a new and improved, or maybe just new, recording device so that we can continue our OChem adventure together. So this is looking at more detail on hybridization and specifically organic compounds. So, carbon's a little bit problematic when it comes to hybridization, or maybe not. The bottom line is, look at here. We know this ground state configuration stuff from chapter 1, and we know this is what the electronic configuration looks like. That basically, the core electrons, we don't pay any attention to them because they're not involved in bonding, but that leaves us with two sets of paired electrons. Well, then how does carbon make any bonds? Doesn't make any sense. So, we know from experimental data that carbon bonds with 4 other atoms. Either it's 4 single bonds or a double bond and 2 single bonds, whatever. It's supposed to have 4 bonds. It doesn't match this ground state electronic configuration. So we have to come up with an explanation. And the explanation is hybridization. In other words, because carbon really wants to have 4 bonds, we promote one of the electrons from the 2s orbital and bring it, as you just saw, into the empty p sub z orbital. Similarly, we unpair the pair in the p sub x and bring one of those electrons to the p sub y. What does this do for us? It gives us 4 unpaired electrons so that, boom, we can have 4 bonds. Now, the other problem with what we understand up to this point about how carbon is, how that atom is, you know an s orbital is a sphere, and then the p orbitals are 90 degrees opposite one another. Well, if that's the case, then if my carbon atom tries to bond and make 4 bonds with a 2s orbital, a 2px, a 2py, and a 2pz, then we're going to have, simply put, 90-degree bond angles. And we know that's not true. As we've learned from VSEPR, they are 109.5-degree bond angles. So how do we explain that? We explain that by saying that all 4 of these orbitals are put into an imaginary blender, if you will, so that they're all mixed up together, and then you pour them back out again to get 4 orbitals that look exactly the same. Because it's 3 parts p orbital and 1 part s orbital, we call them sp3. Okay, so we have an orbital that no longer looks like an s orbital. It's not a little basketball. And it no longer looks like a p orbital. It's not a nice symmetric dumbbell. It's an sp3 that's 25% s character, 75% p character, so it's kind of squatty but still has 2 lobes, yada yada yada. Very important that you understand that I start out with 4 atomic orbitals. I throw them into the blender, and I end up with 4 atomic orbitals. And all 4 of them look exactly the same. So that's hybridization. Now, on to our next fun activity here. I'm stuck. How do I get out of this? I'm working on it. We're going to have some, how do I say, some technical difficulties while I try to figure out what I'm doing. You kind of knew this was going to happen. Get out of that. There we go. Nope, that's really not what we wanted to do. We'll try this again. Okay. So, there we go. Sorry about that. Alright, so we get 4 sp3 orbitals because we threw all 4 of carbon's atomic orbitals into the blender. Who said we had to throw all 4 of them into the blender? So for example, I promote my electrons. I have my 4 unpaired electrons in my 4 atomic orbitals. But what if I just decide to hybridize one of the the 2s orbital and 2 of the p orbitals? I'm going to absolutely positively leave this guy, my last p orbital, I'm going to leave it out of the blender. What do I get? Well, then I'm going to end up with 3 atomic orbitals that look exactly the same because I used 1 s orbital and 2 p orbitals. They're called sp2. I know, we're not very creative in our naming. They each, of course, have 1 electron in them. And then the 4th electron, the 4th atomic orbital, and the 4th electron just stays there unhybridized in the 2pz orbital. So we can play this little hybridization game with as many of the s and p orbitals as we want. All 4 of them, just 3 of them, only 2 of them. As we do this, you want to think about the shapes of the orbitals that will result. And the shapes of the orbitals that result are going to simply be based on what we see with what we started. An s orbital is spherical. The p orbital looks like a dumbbell. So something that has a lot of p character, 75% p character in the sp3, is going to look more like that dumbbell shape. Something that has 50% s character is going to be a lot squattier and more spherical, but it's still going to have the 2 lobes. So that has profound implications with respect to bonding and bond angles, and this complements VSEPR quite nicely. So that's all nice, it's all good, but why in God's green earth does this happen? And it's basically because we said so. No, it's basically because of experimental data. Like I said, we know carbon bonds to 4 things. We know carbon compounds with sp3 orbitals have 109.5 degree bond angles. Everything always falls back to what the scientist measured in the lab and observed in the lab, and then you have to explain it. The other rationale as to why it happens is because it's all good. Everything in the universe always tends towards a minimum energy, right? We want to sit on the couch instead of going out and running around the block. Therefore, molecules want to do the same thing. And even though it takes energy to promote those electrons, I mean, after all, these guys are paired. Why would they want to do this? Well, they'd want to do this because by splitting them apart, which takes energy, I get energy back from making more bonds. So there is a good reason for hybridization. And how you can tell what hybridization is occurring, well, it's all VSEPR and looking at the types of bonds that are in the molecule. So we're going to go through a couple of examples, and then the next mini lecture is just going to be nothing but hybridization examples because it's not the most easy thing to figure out. Alright, so we start with chapter 1, draw the Lewis structure. Figure out what this molecule's bonding patterns look like. Then use VSEPR to figure out the shape of the molecule. Is it tetrahedral? Is there tetrahedral atoms or trigonal planar atoms, etc., etc. And then, as Carty would say, think. Think about the kinds of orbitals that are absolutely required to achieve these bonding patterns and molecular shape. So 2 quick examples. Okay, well, 2 quick examples where we will think about this one atom and bond at a time. First one, this is methylamine, and if we redraw this guy in its full Lewis structure, we know it is C, H, 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 N, lone pair, H, H. Now, what I'm interested in is What's the hybridization of the carbon? What's the hybridization of the nitrogen? Okay, carbon, 4 bonds around it. That means by VSEPR, it must have 109-degree bond angles. Therefore, the only orbitals I know that will allow 109.5-degree bond angles and allow 4 single bonds are sp3. Okay, so the carbon atom must be hybridized sp3. What about the nitrogen? Well, nitrogen-wise, 1, 2, 3, 4, 4 sets of electrons. Therefore, it too needs 4 containers for these electrons. 1 each for each of the single bonds and 1 for the lone pair. So nitrogen as well must be sp3 hybridized. I need 4 containers again, if you will, for my 4 sets of electrons. And I'll just show kind of a dotted line for my 4th sp3 orbital there. This guy also sp3 hybridized. Okay, so we look at the Lewis structure, we look at the bonding pattern, we think about the bonds that are being made. So the overlap here, that we would describe as an sp3 s sigma bond, because it's the s orbital on my hydrogen and the sp3 orbital on my carbon that are overlapping in a head-on fashion to make a sigma bond. Alright, next example. What about something like acetonitrile? No, that's not acetonitrile, that's just HCN. What about HCN? Well, we've already got the Lewis structure there pretty much. Get a lone pair in here and we'll be set. And this time I'm just going to focus on the nitrogen. So our nitrogen, looks like we've got a linear bond angle there. Bond angle? There's no bond angle. What are you talking about? Well, we have 4 sets of electrons around nitrogen, right? No, we don't. We have 2 sets of electrons around nitrogen. This set of electrons, the triple bond, and that set of electrons, the lone pair. So what I'm saying is, those two have to be as far away from each other as possible. So that implies right there, VSEPR says 180 degrees, and that implies right there that it's going to be an sp hybridization. That this is going to be an sp orbital, and that the carbon-nitrogen sigma bond is going to be formed from the overlap of an sp orbital on, I should make that a lot squattier actually, an sp orbital on nitrogen and an sp orbital on carbon. Okay, so this bit is going to be an sp sigma bond. So VSEPR is helping us out here. But more than VSEPR, I want you to, again, think about the atoms involved, think about the bonding involved, and realize that in order for me to have a triple bond, I have to have 2 more atomic orbitals overlap in order to make the 2 additional bonds. So one set of atomic orbitals is shown here. Let's see what, we'll make this kind of a pink. Or not. There we go. So this side-to-side overlap, that's absolutely positively 1 bond. It's a pi bond, formed from the overlap of two p orbitals, one on carbon and one on nitrogen. So now I have two bonds. The sigma bond right here, and the pi bond is shown by the pink. Where's the third bond of the triple bond coming from? Well, that would be coming from another set of p orbitals. Again, each one has one electron in it. And when they overlap, and now I'll change to a hideous green. Okay, so we're making this very colorful anyway. Okay, so that means I now have another pi bond being formed. So the total bonding pattern for this carbon-nitrogen triple bond is 1, the sigma sp-sp bond, then 2 p-p pi bonds. All right, that describes the entire bonding pattern. What's the hybridization? How does this help us? The only hybridization that is going to leave us with, oops, that didn't work, that's going to leave us with the bonding orbitals that we need in order to have a triple bond, we must absolutely have two leftover p orbitals on each atom. So that means the only possible hybridization is going to be sp, because when I hybridize my s and p, I'll end up with two sp orbitals and two leftover unhybridized p orbitals right there. One on each atom. Okay, this will sink in a lot better with more examples, and that's what the next mini lecture will be about. I'll do some alkene isomerization to help you understand why the bonding patterns really matter. We'll talk about bond length and bond strength. That varies with the type of molecular orbitals that are overlapping. Specifically, that the longer the orbital, sp3, that extends furthest from the carbon or nitrogen or whatever nucleus, and the sp is really short and squatty. So bonds with sp overlap are typically stronger than bonds with sp3. But I really think it's time to end with a really bad joke. And of course, this is so obvious. What happened when the red ship and the blue ship collided in the ocean? Why, they were marooned. Get it? Okay, hybridization happens, and we'll have some fun examples in class. See ya.